Hi everyone. Today we're taking a look at high-resolution low vibrational infrared spectroscopy investigation of HCl and DCl. I think it's important to quickly note why using high-resolution IR spectroscopy is key to this experiment, especially because throughout a lot of our undergrad careers, we often think about infrared spectroscopy as something vibrational, where we're looking at large, broad peaks like this. With high-resolution infrared spectroscopy, it's possible to resolve all of the vibrational transitions that occur in those larger vibrational peaks. This is key because one of our objectives is to obtain rotationally resolved vibrational absorption spectrum of both HCl and DCl. And our second objective is from there to determine a set of physical constants and parameters that describe bonding, rotation, and vibration. And right now it looks like a lot, but we'll be able to break it down very simply. Starting off from HCl. So we know that it can undergo a vibration, as can DCl, and we can understand this vibration through the harmonic oscillator approximation. Here, we're able to look at compression or extension by relating x, the change in internuclear separation, to k, the force constant, one of the things we're looking to determine. Also, we're able to relate energy to the degree of vibrational excitation, Planck's constant, and the harmonic frequency, another one of those constants and parameters that we're looking to calculate. In addition to vibration, both HCl and DCl can undergo rotation. We can understand that through the rigid rotator approximation. So here it's possible to relate our energy to the rotational quantum number and the rotational constant. Further, we can express the rotational constant in terms of reduced mass and equilibrium bond length, which you'll notice that term is inertia. Since it's very easy to calculate the reduced mass just from known quantities, that means we can find our equilibrium bond length from our data. That is still not all. In addition to vibration and rotation, it's possible for HCl or DCl to dissociate. And it's important that we consider all of these together because they impact one another. Starting off, we can look at the Morse potential, and you'll notice that on the left, it looks very much like the harmonic oscillator because the internuclear distance can only get so small because of repulsion between the two nuclei. On the other hand, it could get infinitely far if we have dissociation going on. So this model allows us to account for dissociation, and that lets us determine bond energy and the potential energy to the bottom of the well. By bringing in another couple of helpful equations, which rely on variables that we previously defined and a few new terms that account for how these models combine together, we are able to determine our anharmonicity, which is deviation from the harmonic model, and our rotational vibrational coupling constant, as well as D, our centrifugal distortion constant, which accounts for how non-rigidity impacts rotational motion. Which is great. Now we're ready to look at our hypotheses based on this background and the equations. Firstly, we believe that equilibrium bond length should be the same for HCl and DCl because the atomic radii are the same for hydrogen and deuterium. Secondly, and this is based off the equations, the rotational constant for HCl should be approximately twice the rotational constant for DCl because they depend inversely on the reduced mass because of the inertia term. Now we can take a very quick look into our methods, where we had 2.5 grams of potassium chloride in a 25 milliliter round bottom flask equipped with a 3-way adapter and a septum for addition by syringe. Next, we should note the stopcock is open, the tubing is securely clamped on both sides, and connected using a needle to our gas collection chamber. The gas collection chamber also is equipped with a needle for venting because we're going to be producing gas in our chemical reaction, and we want to displace the gas that's currently in there, not create excess pressure. Next, in the preparation of the acid solution, a 1:2 ratio of sulfuric acid to deuterated sulfuric acid. And right here, it's important to go quickly because we want to minimize the opportunity for exchange of our deuterium with hydrogen from water in the atmosphere, because both of these acids are hygroscopic. Next, in the addition, it's important to go slowly. We can also quickly note that it's clamped here, and we didn't have that clamp in the previous picture, but it's important. The addition needs to be slow because, of course, we are producing a gas. So we're going to get this sort of foamy, frothy mixture, and we don't want that to exceed halfway up the flask. Unfortunately, it did. And at that point, it's important to just make absolutely sure that it does not enter the collection chamber because that would interfere with our ability to collect data. Thankfully, it didn't, so we can look at how we collected our data, which was using a Perkin-Elmer FTIR spectrometer. This uses an IR source, a beam splitter, and then IR radiation goes through our sample to the detector and interferogram, where it's possible to process the degree of constructive and destructive interference. Then with the computer, we can go through Fourier transform to get from the time to frequency domain. Here's our spectra. And by taking a first look, it's immediately clear that we have four groupings of peaks made up of smaller peaks. That should make sense because each of these groups represents a vibrational transition, and then each of the little peaks making them up is a rotation. Further, we're able to assign HCl and DCl to each of these based off of their wave number, and overtone versus fundamental based off of both their wave number and their population. So what do we mean by that? Let's take a look at the HCl fundamental transition in a little bit closer of detail. So zooming in, immediately we see that we have two branches. On the left, we have the R branch. On the right, we have the P branch. And before we get into it, we can quickly also note that each of these peaks is a little bit split. And that's because of the two isotopes of chlorine, which have only a very small impact on the reduced mass. So we get just this little bit of splitting there. And we're not quantifying it in this experiment. We can just notice that it's there and understand why it makes sense. Getting back though to the R and the P branch, we see that the R branch involves transitions from J to J plus 1 for V to V plus 1. And the P branch, contrastingly, goes from J to J minus 1 for also transitions of V to V plus 1. This makes the energy spacing different for the R and the P branch, and also nonlinear as you go across either of the branches. We might also wonder about from J to J as we go from V to V plus 1. That would be the Q branch, but in this system and many others, it's prohibited, and we can see that we don't have a peak representing it. Zooming back out, we can quickly look at an overtone. So here we see still an R branch and a P branch with the same relationships between J values, but instead of going from the ground state to first excited vibrational state, the first overtone transition goes to the second excited vibrational state. And if there were additional overtone transitions, they would keep going to later states. We can also see here it has the same nonlinearity that we mentioned, and it's easy to see that as the J value increases in the P branch, our energy gaps are getting farther apart, and as J value increases in the R branch, they're getting closer together. This nonlinearity is very helpful, and we can use it to process our data. Here we're looking at the overtone, R, and P branches, and we can use these equations compared to our third order polynomial regression equation. Here, we can directly determine D and alpha and B just from the coefficients of the terms, the appropriate terms of these equations. And then by setting up a simple system of equations, it's possible to solve for the anharmonicity and the harmonic frequency. That's excellent because from the relationships that we discussed earlier, we are able to solve for the rest of our variables of interest based off of these values. Starting off, we can see that from what we determined directly from our data, we have values for fundamental and overtone for both the P branch and the R branch for HCl and DCl. But to take a better look at the big picture, we can see a summary where we compare just HCl to DCl. We also included, just for convenience of comparison, the percent difference, so we can think about how much they may differ from each other or not, and how that relates to their dependence on mass. First, we can clearly see that the rotational constant depends inversely on the moment of inertia, so the larger reduced mass should result in a smaller rotational constant. And that makes sense. With a smaller moment of inertia, it takes less to undergo a rotation. We can also see a similar relationship of being about double for HCl relative to DCl for other terms that also depend on reduced mass. Contrastingly, the bond length does appear to be independent of reduced mass, which makes sense because the electron configurations, electronegativity, and energy levels, things that control bonding, do not really differ between HCl and DCl. So overall, it was possible to probe the transitions between the allowed vibrational and rotational states and determine our target set of constants and parameters.